I'm delighted to welcome Anusha Krishnan, who will speak on toral symmetries of homogeneous collapsed ancient Ricci flows.
Thanks very much, Carolyn, for the introduction and for the invitation to speak here. So I'll be speaking about some recent work on toral symmetries of homogeneous collapsed ancient Ricci flows. This is all joint work with Francesco Pediconi and Sbiti. Yeah, so this is recent work that we posted on the archive last month. Okay, so let me start. So we are interested in the Ricci flow. The Ricci flow is the following smooth family of Riemannian metrics on a manifold satisfying the following partial differential equation where the metric evolves by negative twice its Ricci tensor. So this is heuristically a geometric heat equation for the metric. You might expect it to have regularizing properties, evolving the metric to a nicer metric over time. So it's good to keep some examples in mind. And the simplest example to think of is Einstein metrics. So if your starting metric G0 is Einstein with the Einstein constant lambda, then under the Ricci flow, it evolves according to the following formula. That is, the metric at time t is just some rescaled version of the initial metric. And a good picture to keep in mind is the round metric on the sphere, which is just shrinking with time and it shrinks and becomes extinct in a point at some finite time. Notice I also wrote negative infinity here. So this solution actually also exists for all negative times, all t less than 0. And this is a special type of Ricci flow solution that we are interested in for today's talk. And these are what are called ancient Ricci flows. So a Ricci flow solution is called ancient if it is defined for all negative times. That is, it's defined on some infinite interval like this, stretching back to minus infinity. You can keep in mind as examples Einstein metrics with positive Einstein constant. So why do we care about ancient Ricci flows? Well, because they model singularities of the flow. So like in this picture over here, you see you start with a round metric on the sphere and evolve it with time, and at some finite time, it becomes extinct. So the flow ceases to exist at this time, at this maximal time t. Oh, by the way, can you see my mouse pointer?
Yes.
Yeah, okay, perfect, thanks. All right, so it becomes extinct at this point t, at this time t. So there's a singularity that occurs where you can't continue the flow beyond that. And we're interested in what happens at the point of singularity. So it's known that at the singular time, the norm of the curvature tensor blows up. However, this could happen in different ways. So here I just give you two pictures of things that could happen for Ricci flows on spheres. So you're supposed to think of both these pictures as the three sphere. And in the first picture, it's the round three sphere that is just rescaling, contracting uniformly to a point. And in the second picture, there's a singularity that is occurring, a sort of neck pinch singularity, where the curvature is blowing up all along this this cylinder, like a line times a sphere of one dimension less. Okay, so for understanding exactly what is happening at the singularity time of the flow, the technical procedure to do this is called parabolic rescaling, where what you're doing is slowing down time and zooming in space around the point of singularity. Specifically, you're taking a sequence of points going up to the point of singularity and rescaling the metric and reparametrizing in time to get a sequence of Ricci flows that converge in some sense to another Ricci flow, possibly on a different manifold, and it turns out that Ricci flow solution is an ancient solution. Okay, so right, so ancient solutions arise while you are studying singularities of the flow. That's why we're interested in them. They are classified. So ancient solutions are classified on surfaces, and also classification results exist in higher dimensions under non-collapsing and positive curvature assumptions. And as a consequence of these classification results, due to the works by several authors, as a consequence of these results, it is known that these are rotationally symmetric under these classification results. Okay, so it's this symmetry phenomenon for ancient Ricci flows that we are interested in today. And in particular, we want to study this in the homogeneous case. Okay, so the homogeneous case seems pretty nice. It's already very symmetric, but it'll turn out that it's possible for it to be even more symmetric. We will see that in the course of this talk. Okay, so now for the rest of the talk, I will be focusing on the homogeneous case. We will be looking at Ricci flows on homogeneous manifolds, and in particular, ancient homogeneous Ricci flows. So here's the setup. M is a homogeneous space, which we write as G mod H. Here, G and H are compact and connected, and little g is a left invariant metric. So it's known that the isometry group of the manifold is preserved under the Ricci flow, and so the flow restricts to a flow through G invariant metrics. So you start with a left invariant metric on your homogeneous space, and as you're evolving it by the Ricci flow, it is still invariant. Okay. We will also be interested in the volume normalized Ricci flow, which I will denote by G tilde. So this is equivalent to the Ricci flow, but it's got by doing some rescaling and reparametrizing in time, so that this flow is through unit volume metrics. The volume is preserved under this flow. So sometimes we will be interested in studying the behavior of our ancient homogeneous Ricci flow by looking at the corresponding volume normalized Ricci flow. Okay, so in the homogeneous setting, the equation satisfied by this volume normalized Ricci flow looks like this. The metric is evolving by negative twice the traceless Ricci tensor. Okay, and this is something special that happens in the homogeneous setting, that this is a gradient flow for the total scalar curvature functional. In this case, the functional that just sends the metric to its scalar curvature. So this is a functional defined on this space, fancy M sub G sub 1, which denotes the space of unit volume G invariant metrics on the manifold. Okay, so in this in the homogeneous setting, this is a finite dimensional space, and the volume normalized Ricci flow is a gradient flow on this space. Okay, right. This functional is special. The critical points of this functional are unit volume Einstein metrics on the manifold, and so this is a problem that has been studied. Deeply studied, and you can imagine that critical points of this functional, which are Einstein metrics, and the search for them has something to do with studying the volume normalized Ricci flow in this space. And so the extensive structure theory developed while studying in the search for homogeneous Einstein metrics also tells us something in the case of the Ricci flow. Okay, so now I'm going to compile some bunch of information that we know about ancient homogeneous Ricci flows. So firstly, we know that for ancient solutions, the scalar curvature is always non-negative. This is something general, not specific to the homogeneous case, but I just mentioned it here. we will say that the flow, the Ricci flow G of t, is non-collapsed if these curvature normalized metrics, where you took the metric G and rescaled it by the norm of the curvature tensor. So if these curvature normalized metrics have a uniform lower injectivity radius bound, uniform in T, we will say that the flow is non-collapsed. Okay, so the non-collapsed case for ancient homogeneous Ricci flows is quite well understood. We know firstly that the scalar curvature goes to some positive number as you go back to minus infinity. And even more, it's known that the parabolic rescaling limit as you go back to minus infinity is unique and is an Einstein metric on the manifold. So this is something special that happens in the homogeneous setting. So this is known by work of Bohm, Lafontaine, and Simon. Okay, so the non-collapse case is quite well understood. So in today's talk, we will be interested in the collapsed case. So what's known there? In the collapsed case, the scalar curvature of the volume normalized metric goes to 0 as t goes back to minus infinity. And it's known that the manifold must be the total space of a homogeneous torus bundle. So the manifold G mod H must fit into this structure of a homogeneous torus bundle, where T is some torus inside the normalizer of H mod H. Okay, so right, so this collapsed case corresponds to 0 Palais-Mail sequences for this functional on the space of unit volume G invariant metrics. And so by the theory developed by Bohm and Ziller, it's known that the manifold must fit into this homogeneous torus bundle picture. Okay, so in the collapse case, we have some more structure for the manifold. What else? There are a number of examples of ancient collapsed homogeneous Ricci flows. So there are several examples on spheres, on homogeneous spheres, due to works by a number of authors. And I will also mention this result by my collaborators, Pediconi and Sbiti. It shows that you always have an ancient collapsed homogeneous Ricci flow on G mod H whenever you have G mod TH admitting an Einstein metric for some maximal torus inside the normalizer H mod H. Okay, so right, so there were these several examples on spheres and on other manifolds, and then Pediconi and Sbiti generalized it. Generalized it to this construction. Okay. And in particular, in their result, this ancient Ricci flow that they find on G mod H, as you go back, as t goes back to negative infinity, what happens for the volume normalized flow is that it is shrinking the torus fibers, and in the limit giving you this Einstein metric on the base. Okay, so there's some more structure known there. Right, so we will be interested in finding extra symmetries or these toral symmetries in the collapsed case. And before I say more, I'd like to illustrate the ideas or the kind of phenomenon involved by an example. Okay, so in our example, the manifold we are looking at is the 3-sphere, which you should think of as the set of unit quaternions. Okay, so the 3-sphere is a Lie group. It acts on itself by left multiplication. And that's the G mod H we are interested in this example. Okay, So, right, up to isometry, you can assume that the metric is diagonal in bases spanned by these imaginary quaternions I, J, and K, and the metric on the tangent space at the identity has these three eigenvalues X, Y, and Z. Okay, so this is what a left invariant metric on this manifold looks like. And now we will be interested in looking at the Ricci flow behavior. So I'm going to state things in terms of the normalized flow. So, okay, so it turns out that this diagonal form of the metric is preserved, and I'm going to denote the eigenvalues of it like so. Okay, so what is known due to work of Cao and Saloff-Coste is that if you have an ancient homogeneous Ricci flow on the three sphere, then the eigenvalues of the metric must satisfy this following relation. That is, the two largest eigenvalues must be equal all along the flow. Okay, so, and there's more. So, right, to state that more, I should remind you that we have a fibration like this. So S3 fibers over the two sphere with circle fibers, where the circle, where you can take this circle of the unit quaternion spanned by 1 and I. And so more in their result says that if the, wait, so let me remind you that if the smallest eigenvalue is also equal, so if all three eigenvalues are equal, that's the round metric on the three sphere, and we know how the round metric evolves. It's Einstein, and it evolves just by shrinking. And on the other hand, they show that if the smallest eigenvalue is strictly less, then what happens is that as t goes to negative infinity, the circle fiber shrinks, and what happens is that in the Gromov-Hausdorff limit, you get a round metric on the base, on the two sphere. Okay, so we are going to try and interpret this result in terms of Toral symmetries. So this circle S1, of course, it's a subgroup of S3. It's acting on S3 by left multiplication isometrically. But just as a Lie group or as a Lie subgroup, it could be also acting by right multiplication and or even by left and right multiplication at the same time by the adjoint action. And let's see what happens under the adjoint action. So if I look at the action of this group element Q theta by the adjoint action on this tangent vector J, then the length squared of the resulting vector, you can compute it out like so. It has the following expression. So these are these computations are not difficult to do. I just wanted to mention them to give some more concrete picture. Right, so from this you see that y equals z can be interpreted as the adjoint action being isometric, in particular right multiplication by S1 also being an isometry of this evolving metric. Okay, so the upshot is that if you have an ancient collapsed homogeneous Ricci flow on the three sphere, then right multiplication by the shrinking S1 fiber is also an isometry. Okay, and this phenomenon more generally is what we are interested in. So this is also the behavior in all known examples, particularly that the as you go back, as t goes back to negative infinity, the volume normalized matrix G tilde, they are shrinking the fibers of a homogeneous torus bundle and converging to an Einstein metric on the base in the Gromov-Hausdorff topology. So here is my cartoon of what happens as t goes back to negative infinity. This is what we are interested in. Okay, so we may ask if the same, if the symmetry phenomenon we saw on the previous slide happens in general. So we may ask, in general, is the evolving metric invariant under the right action of the torus, of the torus that is shrinking? And indeed, this is true in all known examples. And the theorem I want to talk about today is what we prove is that under certain assumptions, the answer to this question is yes, the metric is invariant as well under the right action of the collapsing torus. Okay, so this is the main theorem for today. In the remainder of the talk, I want to explain what these assumptions are. So there is one geometric assumption and one algebraic assumption. So I will explain what those assumptions are and why we need them, and then say some words about the proof of the theorem. Okay, so let me proceed. So first, I need to introduce some notation. So probably you are familiar with most of this, but I just want to set the notation. So G mod H is our homogeneous space. G and H are assumed compact and connected, and we denote by these Gothic letters the corresponding Lie algebras. We fix some bi-invariant inner product Q on the Lie algebra G, and we denote by M the Q orthogonal complement of H inside G. So M now, notice, is identified with the tangent space to the manifold. The isotropy group or the stabilizer group H acts on the tangent space, acts on M by the adjoint action. Okay, and under this action, M splits into add H modules, and we denote by M naught the trivial module for the add H action. And it's a fact that the trivial module M naught is identified with the Lie algebra of this group, the normalizer of H mod H. Okay. Further, whenever you have an abelian subalgebra inside M naught, inside the trivial module, there's a corresponding torus fibration, like so, where the torus T is the connected Lie subgroup of normalizer H mod H, which has Lie algebra little t. Okay. Further, I should observe that the gauge group NH mod H acts on M by the adjoint action, and it preserves the decomposition of M into M naught and M naught perp. And we will use the notation, we will use the letter phi to denote decomposition of M into Q orthogonal and irreducible add H submodules. And we will number them from 1 to L. So, right, of course, you may have several different decompositions. So we will want to specify which one. We will use the letter phi. And we will also write, we'll use the letter L naught to denote the dimension of the trivial module. Okay, so L naught is the dimension of the trivial module, and here MP are each one-dimensional modules. Okay, right. So the letter P will always be used for indices corresponding to M naught. Okay, now you say that a basis for M is phi adapted if it respects the decomposition phi. Okay, and finally, we will be interested in decompositions phi that diagonalize the metric, like so. Okay, so they diagonalize the metric, and xi's will denote the components of the metric. Okay, so that was some notation. Now let me talk about, I want to lead up to the geometric assumption in our theorem. So I mentioned earlier that if you have a collapsed ancient Ricci flow, then as t goes to negative infinity, the scalar curvature for the volume normalized flow is going to 0. And I also mentioned that by the work of Pullman and Ziller, it is known that the manifold fits into this homogeneous torus fibration. Okay, but this is an abstract result. It just tells you that if you have a zero Pellissmale sequence on your manifold, then the manifold must have this structure. But we want to know exactly what this torus is along the Ricci flow, how it relates to the geometry, the evolving geometry along the flow, and more light is shed on that by this result of Pediconi. So he showed that if you have any, or as a consequence of his work, we know that for any time sequence going to negative infinity, there is a limiting abelian subalgebra inside M0, on which the renormalized, the volume normalized metric goes to 0. Okay, so what do I really mean by this? I should be more precise, so I will explain. Specifically, what is known is that for each n, so for each time along your sequence of times going to negative infinity, there is a decomposition that diagonalizes the metric. Of course, this decomposition a priori just it depends on the sequence, depends on the time. What is known further is that the sequence, this sequence converges up to subsequence. It converges to a limit decomposition, which we denote by phi infinity. And up to reordering, there is some number between 1 and L0. L0, remember, was the dimension of the trivial module, and some delta positive, so that the first S indices, the metric goes to 0, and the remaining indices, the metric is bounded away from 0. And moreover, in the limiting decomposition, the sum of these first S modules is an abelian subalgebra of M0. Okay, so this is in detail what is known due to work of Pediconi, but the limiting abelian subalgebra, it could depend on the choice of sequence, and we are interested in the Ricci flow. So of course, along the Ricci flow, you could take some sequence of times that go to negative infinity, and you obtain some corresponding limiting abelian subalgebra, but we would like something that happens all along the flow. So, I mean, geometrically, it could happen that this torus that is shrinking, so C actually corresponds to the torus that is shrinking backward along the flow, that could be oscillating within the gauge group as I mean, depending on time. So we'd like a fixed torus, and when we are dealing with the Ricci flow, so we need to make a stronger assumption, which we call a strongly shrinking torus. So let me say what that definition is. So this is our geometric assumption that will feature in our main theorem. So a strongly shrinking torus for this ancient collapsed Ricci flow is defined to be a torus inside the gauge group, satisfying these following three conditions. So firstly, the restriction of the metric to the torus goes to 0. Oh, this is a typo. This should be T goes to negative infinity. Sorry about that. Okay, and the second condition says that T and its Q orthogonal complement inside M are also G orthogonal for all times. And the third condition says that on the complement of the torus, the metric is bounded away from 0. Okay, so this is saying that there's some fixed torus along which the collapse is happening as you go back to minus infinity. And in this case, we say that G of T collapses along the strongly shrinking torus T. Okay, so as I emphasized, by what we know by work of Permangsiller and Pediconi, this torus could depend on sequences. So in general, it's not clear if we have a strongly shrinking torus. So in general, this is an extra assumption. However, there are some cases in which the existence of a strongly shrinking torus is guaranteed, and we prove this theorem. Okay, so what does this say? If we have a collapsed ancient solution to the G homogeneous Ricci flow, and we are in one of these two cases, either the trivial module is just R, or the trivial module is isomorphic to SO3. So notice these are both the cases where the trivial module has rank 1. And in the second case, we also need to assume that the complement of okay, sorry, this is another typo. Sorry about that. So this should read M. So this is the complement of M naught inside M. So yeah, so we also assume that that does not contain any pair of equivalent irreducible ADH modules. Then the conclusion is that M collapses along a strongly shrinking torus. Okay, right. So for example, this happens in, one instance of this is the example I discussed, the Ricci flow on S3. In my list, in the list of examples on the previous slide, there was these spheres of dimension 4n plus 3 given by SP n plus 1 mod SPN, studied in work of Sbiti. So they also fall into this this setup, right? So in these cases, we are guaranteed a strongly shrinking torus. Okay, so much for the geometric assumptions. Next, I will say some words about the algebraic assumption. Okay, so this assumption is going to be an assumption on the decomposition. So I need to make some definitions. We say that a decomposition of M is stably Ricci diagonal if every phi diagonal metric has phi diagonal Ricci tensor. So, right. So phi diagonal every phi diagonal metric has phi diagonal Ricci tensor. So this this notion of a stably Ricci diagonal basis was, to my knowledge, it was introduced by Payne and used to study the Ricci flow on Lie groups. And later Lauret and Bill gave an algebraic characterization for this condition in the setting of nilpotent Lie groups, or nilpotent Lie algebras. Right, so characterizing it by some condition on the Lie brackets. And yeah, I also gave a Lie algebraic characterization of it in the setting of compact semi-simple Lie groups and compact homogeneous spaces. Okay, so right, so just to mention that there is some Lie algebraic characterization of this condition. Why is this condition important? Because it ensures that the metric flows through diagonal metrics. In other words, the eigenspaces of the metric will not be changing under the Ricci flow, and that is important for our analysis. Okay. Yeah, just for completeness, I mentioned also that if we have a stably Ricci diagonal basis, and then the Ricci tensor is diagonal, then the Ricci eigenvalues are given by the following expression, which is, you can see it's some algebraic expression in the entries of the metric, and these coefficients, bracket ijk, are some constants that come from Lie algebraic information according to this following expression. Here, EIs from a Q orthonormal basis for M. Okay, So that was definition number one. And next, a decomposition of, again, a decomposition of M is said to be normalizer adapted if the infinitesimal action of the gauge group permutes the irreducible modules Mi. Okay, specifically, what we get out of this is that if we have a normalizer adapted decomposition, so let Vp be a generator. So this is a generator of some trivial module. Then either under the adjoint action, Mi gets sent to some other Mj, in which case we will write, we didn't define this map on indices, and we write that Vp of I is J, or the adjoint action of Mi is just 0, in which case we will write Vp of I is I. Okay, so just to emphasize, normalizer adapted says the infinitesimal action of the gauge group permutes the irreducible modules, and which permutation it is depends on which index P we chose inside the trivial module. Okay, and Vp denotes that map on indices. Okay, so since we are interested in showing toral symmetries of the flow, and the torus sits inside the gauge group, yeah, this should tell you that it is useful for us to somehow control the action of the normalizer. So the action of the normalizer should not be too wild, and this is the assumption we make in order to achieve that. The stably Ricci diagonal assumption, I said, ensures that the metric flows through diagonal metrics. Okay, and the combination of both of these is what we need to assume. So we make the definition of strongly Ricci diagonal. We say that a decomposition is strongly Ricci diagonal if it satisfies both of these conditions. It is stably Ricci diagonal as well as normalizer adapted. So this is the algebraic assumption we need. And now I can state the main theorem. So, right, so this is what we show, that if you have a compact homogeneous space, G and H are compact and connected with isotropy representation that admits a strongly Ricci diagonal decomposition. So first we have this assumption on the decomposition. Then we say that G, we assume G is an ancient solution to the homogeneous Ricci flow on the manifolds, so that the starting metric is diagonal with respect to this given strongly Ricci diagonal decomposition. And we are assuming that our flow, our ancient solution is collapsed, and we're assuming that the collapse happens along a strongly shrinking torus. Then under these assumptions, we conclude that the metric is invariant under the right action of the torus as well. Okay, so this is the precise statement of our main theorem, that collapsed ancient homogeneous Ricci flows have these toral symmetries. Okay, so I'd like to say a few words about the proof, or some of the ideas in the proof. So we introduce the following tensor, which we call the submersion tensor. So this tensor is defined for, okay, so it has the metric and some torus inside the gauge group, and it takes as its input in the first factor a vector inside the torus, and the other two factors are just vectors in M, and gives you a number in R according to the following expression. Okay, so what this tensor is really is it is telling you the infinitesimal version of the adjoint action of T on the manifold. Okay, so in particular, the vanishing of this tensor is equivalent to the torus T acting G isometrically on the right as well. And the terminology for this is that G is a submersion metric. So yeah, so another way to say this is that this tensor vanishes if and only if G is a submersion metric with respect, is a submersion metric for the torus fibration with fiber T. Okay, so that's why we call it the submersion tensor. And we are interested in showing that the submersion tensor is just dead zero along the flow. So in particular, we show that under the assumptions of the theorem, the following is true. Firstly, that the norm of the submersion tensor goes to 0 as T goes to negative infinity. And also that the norm of the submersion tensor is monotone, non-increasing in time. Okay, so the combination of these two facts, asymptotically you are gaining, or asymptotically you have toral symmetries, as well as this quantity is monotone, non-increasing, it tells you that in fact it must just have been dead zero. So that is the that's the rough idea. So let me mention some more details about this. So for the proof of one essentially relies on a work of Pediconi, which I mentioned before. So in that paper, he shows also that asymptotically you have some toral symmetries, which I will explain. So here's some notation. You pick a generator VP inside the torus and let SP denote the submersion tensor, where in the first entry you put that particular generator inside the torus, and pick a Q orthonormal and phi adapted basis for M. Then if I is an index so that the adjoint action of VP on MI is non-trivial, it's non-zero, we denote such indices by I sub T. And so now if I is such an index and you have, you take a basis element inside that corresponding submodule, then you get a non-zero value for SP applied to E1 and E2 only if E2 is in the module, the submodule that is the image of MI under the add VP action. Okay, so remember the normalizer adapted assumption told us that the add VP action permutes the irreducible submodules. In fact, it permutes the irreducible submodules within each equivalence class. And all right, so using this, we see that these are the only non-zero terms inside, only non-zero terms for the S tensor, and we can compute this expression for the norm of the S tensor in the direction of VP as follows. So it has here those the bracket constants. So this is purely Lie algebraic data times this quantity theta pi, which depends on the metric, like so. Okay, and okay, right. So we are evolving things by the Ricci flow. So in fact, all these xi's are dependent on time, and by applying results from Pediconi, we can see that the limit in the limit as T goes to negative infinity, this ratio goes to 1. So you should think of this as the modules that are intertwined by the add VP action. The metric on them is asymptotically becoming more and more equal. Okay, so now it's clear from this expression for theta pi that this result of Pediconi implies that asymptotically the norm of SP is going to 0. So that is part 1. And for part 2, the monotonicity result. So that is the main new thing in our paper. So let's say some words about that. Okay, it's convenient for us in this part to work with positive times. So I'm just going to write tau for negative of t. So tau is now taking values in 0, infinity. And we are trying to study the monotonicity of S. So we need see this expression for the norm of the S tensor. We need to study the monotonicity, or we need to look at the derivative of the theta pi's. Okay, so we have the following expression for the derivative of the theta pi's when the metric is evolving by the Ricci flow. So you see the Ricci eigenvalues come in here. Now, consequence of the normalizer adapted condition is the following fact, which is very useful for us. So what this is saying is that if the add VP action on MI is non-zero, it gives you another module. It gives you a non-zero module. So MI and MVPI are intertwined by the add VP action, and MJ and M sub VPJ are intertwined by the add VP action. Then the following two bracket constants are equal. Okay, so another way to say this is that the normalizer adapted condition implies some symmetries in these bracket constants. And recall, these bracket constants appeared in the expression for the Ricci eigenvalues. And so as a result of this lemma, we can use this lemma to collect together the terms in this term, the difference of these Ricci eigenvalues. And then we estimate separately the terms that contain some Toral indices and the completely non-Toral terms. So yeah, so there are some technical estimates there I don't want to mention, but just say this is the idea. And now I will mention the key estimate that is our monotonicity result. So for any tau non-negative, we define iota, which depends on P and on tau, to be the index that satisfies the following property. It's the index for which theta P iota is the maximum amongst all the theta pj's. Okay, so it depends on time, and so at some time tau, it is that index for which the corresponding theta P iota is maximal. Okay, and our key estimate is to show that there is some constant delta, which depends only on Lie algebraic data. M is the dimension of the manifold. And there's some time, so that we have the following expression. The time derivative of this maximal theta p iota is bounded from below by this expression, which you can see involves the norm of the submersion tensor. So in particular, if we had some time when the submersion tensor was positive, so if we had some time when the norm of the submersion tensor was positive, then at that time you see from this estimate that the maximal theta pi must be non-decreasing. Okay. And so this contradicts our part 1, which said that the norm of the S tensor goes to 0 as tau goes to infinity. Okay, so that concludes the proof. These are the just sketch some of the ideas in the proof, and let me finish up by mentioning some examples of our strongly Ricci diagonal condition. So they come from this Lie algebraic definition of strongly nice. We say that a Q orthonormal basis for M is strongly nice if there is a decomposition so that the basis is adapted to that decomposition, and if you have two equivalent modules, two distinct equivalent modules, then the following holds true. the following the algebraic terms vanish. Right. I also say that in some previous work I showed that the condition stably Ricci diagonal is equivalent to a condition called nice, which is a condition slightly weaker than this, but this one is useful for us for generating examples. Okay, and we show that if there's a strongly nice basis that is phi adapted, then the decomposition phi must be strongly Ricci diagonal. And as a result of that, we get the following, we get several examples of homogeneous spaces that admit strongly Ricci diagonal decompositions. For example, SON mod products of block embedded SONs, these UN mod U1 UN minus 2 when block embedding, SPN mod, a product of SPPKs in block embedding. By the way, this example fits into the framework of our other theorem. That is it has a rank one trivial submodule, etc. So it in fact admits it has a strongly shrinking torus, as well as alpha spaces and several other examples. Okay, so we have all these examples of strongly Ricci diagonal decompositions, which was one of our assumptions in the theorem. And finally, let me mention that using the strongly Ricci diagonal assumption, we can also adapt the previous work of Pediconi and Sbiti to construct collapsed tension solutions that shrink a non-maximal torus. So that extends the scope of their theorem. Right. So whenever you have an Einstein metric on the base of a torus fibration, and you also have in place the strongly Ricci diagonal assumption, you can get examples of collapsed ancient homogeneous solutions. Okay, so this ties in also with existence of Einstein metrics on homogeneous spaces that are the base of a torus bundle, and so there are potentially other interesting directions for study over there. Okay, so that's all I had to say for today. So thanks very much for your attention.
Thank you for a really interesting talk. Are there questions?
Anusha, I have a question. Can you go back one page?
Yes.
So in these examples you list here where it's strongly Ricci diagonal, is the other assumption also satisfied? So on these examples, do you get that the Ricci flow has the properties you want? Or is the other assumption missing? I forget what all these assumptions were.
Okay, yeah. So in this case, in this example, we are guaranteed that you have a strongly shrinking torus. That is, if you have a collapsed ancient homogeneous Ricci flow, then the collapse must be happening along a strongly shrinking torus. So in this example, we have that.
So that is the torus one dimension, right?
Yeah.
In this case, the torus one dimension.
Yes. Yes, that's right. This you could think of as a generalization of the space studied by Sami. So that was also rank one, like so. SPN mod SP of dimension one less. So this is kind of a generalization of that.
So for the Alvaro space, the normalizer of H mod H is also one dimension. So M0 is one dimension.
Yes, that's right.
Does that also fit into this category then? With
yes, that's right.
Okay.
Yeah. So if you have an ancient collapsed flow, then it's guaranteed to have a strongly shrinking torus, and then yes, you can conclude the extra toral symmetry.
I see. Can you maybe go back to page 9, just to recall the the theorems you had on page 9?
Yeah, sorry, scrolling
Is
really
that the
fast.
right page?
Yes.
Okay, so like in this case, when M0 is R,
Mm-hmm.
so then the normalized of H mod H is one-dimensional,
Mm-hmm.
and the torus can't change. The torus has to be fixed under the flow.
Yes.
M0 is one-dimensional.
Yes.
So in that case, it has to shrink along that R factor
Yes.
and not along the others.
Yes.
So doesn't that already follow from some of the other results?
This one?
What do you have to prove in that case?
In this case, you don't have, there's nothing to prove.
It follows from previous results. So when it's SO3, then the one-dimensional torus could change in that
Exactly.
SO3.
Exactly. So what is special about SO3 is you can assume the flow is through is diagonal on M0, and then you use the result of Pediconi that this limiting torus, the limiting space on which the metric is going to 0 is abelian. So you have something abelian inside this, so.
But that could change a priori.
Yes, it could change. It could change, but we show, we show that the order of the eigenvalues is preserved.
So if I assume that all the modules in M0 perp are inequivalent, and most or all of your assumptions satisfied under that strong assumption, or?
Sorry, so can you say that again,
please? Assume
please?
all the models in M0 perp are inequivalent.
Yes.
As models. Then you can drop some of these assumptions, right?
Which assumptions?
I don't know. Go to the next page. I forget what they were.
Some of these assumptions, you mean?
So that is Ricci diagonal automatically.
Yes. It is.
Is it normalized
it
adapted also automatically? That's also true. It's also normalized adapted. It's inequivalent.
Yes, that's right. But you can have equivalent modules inside M0.
Okay, so assuming that so that's a special for rho equal to 1 or whatever you call it. The one-dimensional ones could not map from one to the other, but rotate it somehow or something.
Yes.
Okay.
I'm not sure. Maybe I'll have to think about this. Maybe it is also, maybe it's easy to see that this holds. But yes, you do have equivalent modules inside M0. So there is something to check.
Okay.
Yeah.
Thanks. Very nice talk.
Any other questions? If not, thank you again. It was really
thank you very much.